Please take your seat. We will start the second day of the workshop. Let me first introduce myself. My name is Juraj Kosek and my affiliation is in Prague and in Pilsen. So we are hosting this workshop and the event. First of all, let me welcome you to the second day of this workshop. And today we will illustrate again the crucial role of redox-flow batteries in energy transition. And we will concentrate on the achievements of the HIGREEW Workshop project. That means today most of the talks will be really about what we so far achieved in organic redox-flow batteries, starting from chemistry, going through membranes, electrodes, some design issues, scale up, all the way up to the practical demonstration and techno-economical analysis. First of all, let me again mention that it's a hybrid event, that we have something like 50 to 60 in-person on-site participants and over 140 online participants that are connected via Zoom. So thank you everybody for joining us. As I said, I will today be the main chair of the sessions. And today the program has first the public session. It's all the way up to the lunchtime. And after the lunchtime, there is a closed session just for the HIGREEW project and for the advisory board. And after the afternoon session, we have an excursion to the pin flow facilities, which is a local company active in redox-flow batteries. Please today wear the mask except of the speakers and except of the refreshments. And the conference is, as I said, with the lunch, and then there will be the private session. Of course, I shall speak something like the welcome message for the 10 minutes, and it's quite difficult to talk about anything without the slides. So I will ask, please, can you switch to the next slide? So it's just the one's introductory, and if you can push the next slide. So I hope that after yesterday, so in order to not obscure the slides, I will probably move this one to the side. I hope that after yesterday dinner that you are charged, but not overcharged with the energy. So we have the energy content everywhere, even in these drinks. So please get to the next slide. And yes, just this one. And yesterday we were discussing many options and many problems in energy transition. One of them is the intermittency of the wind or photovoltaic based power. And there are, of course, many strategies how to mitigate them. I am listing just a few of them. Of course, there are many more. And we were like concentrating mostly yesterday on the energy storage and were not mentioning that much these other strategies. And of course, energy storage to be really practical, we need it to be economically feasible, plus a number of other properties. Please, next slide. Of course, up until now, the central role, not in energy storage, but in really mitigation of the intermittent power, was played in Europe by gas power. This is a statistics from 2020, when Great Britain was still part of EU, and you can see that the gas power generated more than 540 terawatt hours of energy in Europe. So it's really quite significant. Nowadays, with the rising prices of the natural gas, it's quite an issue. Of course, some countries or companies have long-term contracts with suppliers of natural gas, and it's quite a geopolitical issue. So, but there are some regions that are quite sensitive. Please, next slide. You can see what's going on with the price of natural gas, especially in recent months. So there were quite a few spikes. One was in October, one just before the Christmas. And yesterday in the morning when I took a look, so the actual yesterday price was 196 euro per megawatt hour of natural gas. So it's really a number which is quite scary. In case if you consider efficiency of Rankine cycle, let's say 40%, it can be larger. So then the price of the electricity would be 2.5 times larger, just based on the cost of the natural gas. So we can see that it's quite risky to bet everything just on natural gas, which was the politics of European countries and also of many companies in Europe over the last period of, let's say, 20 years. And we can see now that this politics can be quite risky at certain situations. And there, please, next slide. Otherwise, people often discuss another competitor. Another competitor is lithium batteries. And of course, we can praise them for a really large achievement. In case if we take a look on what was the price of lithium batteries over the period, let's say, of last 10 years, this is some price per kilowatt hour of the lithium storage. So it looks just fantastic. And it's really helping electric cars to achieve their goals. And they are really getting close to the price to the combustion engine cars. Please, next slide. However, there are also some clues. In case if we take a look on the current lithium price, and this is current price in Europe. In Germany, it's even in China, which produces more than 70% of lithium batteries. The price is currently even larger, the spot price. So today, or over the last half a year, everybody is discussing more or less that it is at least slowing down the price plunge of lithium batteries, and that really they may not be that competitive as they were thought to be, let's say, 2 years ago. So the situation is also quite changing. So the blue line is really the actual price, and the rest, the gray, is just the forecast or maybe a crystal ball forecast or whatever, based on many different sources. Please, next slide. With respect to lithium batteries, Europe is just sleeping and doing nothing. Over 70% of lithium batteries are produced in China. Then there is some Indonesia or Malaysia, maybe something in the United States. In Europe, there are barely just a few gigafactories. That means it's really not catching up at all. Even the current production of lithium batteries and the expected one in 10 years is really good for development of electric mobility, but still, even if we put all the lithium batteries to electric cars, then we'll be able maybe to support 25% of cars, I mean passenger cars, produced annually in the entire world. Maybe it's a good for 25 million of cars per year, what is going to be produced in 2030 in lithium batteries, but not more. So it's not a complete switch to electromobility just based on lithium-ion. Please go next slide. People often discuss also hydrogen as one of the available options. Of course, there is often a confusion in between blue and green hydrogen. The green one is the one really based on renewable power. It means either wind or photovoltaic on electricity. The blue hydrogen is just based typically on natural gas again. And we are again interested in price, not what is the wishful thinking. Maybe one day it can become cheaper, but what is the actual price on the market? It's maybe 16 or nowadays 14 American dollars per 1 kilogram. 1 kilogram of hydrogen is approximately 40 kilowatt hours plus minus something. So it's quite expensive and not really competitive. So next slide. And this is the final slide of the introduction. And after that, we will continue the program. So the redox-flow batteries are real contender in the business for energy storage. One of their advantages, the long-term stability and the lifetime. Of course, there are some technical issues that will be addressed today in the talks, especially with the organic redox-flow batteries. But one of the take-home messages for anybody listening us is that the redox-flow batteries are really one of the viable options, both economically and technically. And let me finish this welcome introduction. Let me invite the first speaker of the session from the HIGREEW project, who is Eduardo Sanchez, and who will talk mostly about the chemistry which is involved in the organic redox flow batteries. So Eduardo.
Hello, good morning, everyone. So in the next few minutes, I'm going to talk a little bit about the chemistry that is behind this HIGREEW project. We will go from chemistry selection to electrolyte development. This work was done within the different partners in Work Package 2, as a special mention to the University from Madrid, West Bohemia, and PMFlow as well. So we come back to the question that has been around during all these couple of days. Why organic redox flow batteries? So we say that vanadium is a strategic material and it has a really volatile price. So in contraposition, what we have is aqueous organic redox flow batteries, which are based on earth-abundant materials and are tunable in terms of redox potential and solubility, and can even minimize the crossover. So this is why we go to organics. So in an ideal scenario, what could be the electrolyte for aqueous organic redox flow batteries? So we have to divide the targets in two sides. On the one part, we have the active materials, and the other side, we have what is referred to the electrolyte and the battery. So related to the active materials, we have to focus on the cost of the active material, what the solubility of the compound, chemical and thermal stability to have a wide range of operation window, reaction kinetics, and cell voltage, in the sense that we have to find a couple of redox pairs that have a redox potential that once that they are coupled can lead to a cell voltage over 1 volt. In the case of the electrolyte and the battery, we have to focus on the energy cost, the as high energy density as possible, capacity retention, which is in our project focused at 8,000 cycles. And in terms of efficiency, this is translated into the electrolyte based on the conductivity, viscosity, and also the pH, as we want to work in neutral pH. But sometimes we have to find a balance in this, and there is a compromise. So the guidance should be put by the set plan targets that are an L cost of 5 cents euro per kilowatt hour per cycle at 10,000 cycles, while we keep the focus on scalability, safety, and environmental impact. So said that, our planning was to first go for the design and synthesis of active materials, then we turn into the electrochemical characterization, and in a final step, we evaluated the scale-up process and as well as the electrolyte development. Related to this selection of the active materials, we have a broad spectra, wide options for this one, from phenazines, anthracenones, then we have some biologens for analyte as well, some quinones can be applied as well as catholites, iron-based compounds, and tempo derivatives. So in our case, since we want to focus on neutral pH, what we have is that biologens and iron derivatives as well as tempo derivatives are the ones that are looking more promising. So, but in this sense, we started our plan with indigo-based compounds, which potentially can be applied as negolite and catholite at the same time. In this sense, we evaluated 6 different compounds in which we were playing with the substitution in the ring by using different sulfonate, introducing sulfonate group in the different positions, and as well also we played with the counterion, changing the solubility of the compound by means of introducing ammonium cations, hydrophilic ammonium cations. In the case of the biologens, we evaluated 11 compounds guided by some DFT calculations, which allow us to understand better the stability and reversibility of the process. In the case of nitrogen position, we evaluated both 2,2-bipyridinium salts and as well 4,4-bipyridinium salts. And here we introduced some different substituents to boost the solubility. So that was ammonium and sulfates. And in the case of the 2,2-bipyridines, we played with the linker between these two nitrogens. We played as well with some different substitutions in the ring to increase the aromaticity, include some alkyl moieties, ether moieties, or carboxylates. In the case of tempo derivatives, what we play is with the substitution in the 4th position and 3rd position of this ring, and also with the kind of linker that we have in this position. So it could be ether, base, anamine or ammonium substitution, and some alkyl linkers to have a separation between the hydrophilic side and the ring. In the case of the ammonium ferrocyanide, this was much more straightforward as we focus on changing the cation that we were using. In some cases, we were using what we call multiple cation salts, as we will have a mix of these different alkaline metals. So when we move to the electrochemical characterization, we started with indigo. Here we have depicted an example of this compound. We have the 2 sulfonates substituting the indigo scaffold, and then we have 2 ammonium cations as hydrophilic moiety. Here we can see in the cyclic voltammetry, this is the black traces corresponding to the acid compound, while in the other cases we have all those compounds that have a lower redox potential, that are the ones with already some cations as coordinating to the sulfate. In all the cases, we see that the cycling is stable at the neutral pH, that we have a redox potential between minus 0.2 and 0 volts versus standard hydrogen electrode, fast kinetics, and common diffusion coefficient for this kind of molecules. The problem was that this molecule was not reversible to be employed as catholyte. So we turn it into biologen, and here are some of the products that we evaluated, like 4,4-bipyridinium salts and 2,2-bipyridinium salts, as we mentioned, with ammonium and sulfate groups, and as well here playing with the length of the linker between the two nitrogens and the substitution pattern in the ring. So here what we can clearly observe in this graph is that the redox potential of these red traces and blue traces that correspond to the rings with the separator of 3 ethylene moieties can lead to lower redox potential, which is really interesting later to be applied in the cell. So we see that all those show stable cycling. We have a wide range of operation of redox potential depending on the structure, and again, even faster kinetics than the indigo compounds, and same values for diffusion coefficients. So next we turn into the catholyte, and here we have the comparison between tempo derivatives and ferrocyanide. Here we can observe how the traces for the ferrocyanide is showing a much lower redox potential, which is less interesting for later application. And in the case of the tempo derivatives, it is ranging between 0.8 volts and 1 volt. However, some of those materials were not showing a stable cycling, as for example, the C12 material, which is bearing a mesylate anion and a short linker between the hydrophilic moiety and the cycle. So here in comparison for the rest of the properties, all those compounds show good kinetics and good coefficient diffusions. So based on these cyclic voltammetry studies, we move it into the evaluation in cell. So that's why, based on previous study, we focus on the use of B13 compound and tempo derivative C11 redox pair, which would lead to a cell voltage of around 1.5 volts. So here what we observe is when cycling that the capacity decay is quite fast, and we attributed this to the use of this B13 2,2-bipyridinium salt. To confirm this, we did evaluation using this confirmed, this compound, which the stability is well confirmed in the literature, this 4,4-bipyridinium salt, in which in this graph we can clearly observe how the stability of this compound, just focus on the black traces, is that the B21 compound coupled with our tempo derivative is showing a really low capacity decay, less than 0.01% per cycle, while in the case of using this 2,2-bipyridinium salt, the capacity decay is dramatic. In this sense, with these redox couples, we have a cell voltage of around 1.3 volts. So doing a summary of the different families of compounds that we have evaluated, we can see that all of those have the strengths and some weaknesses. In this case, in the indigo derivatives, we see clearly when evaluating as well the solubility and the viscosity that this is not what we wanted for our project, because the redox potential of this compound is quite high as well, viscosity is quite high, and again, we cannot employ this as a beam functional material. That's why we selected the biologens for being employed as anolite. In this case, we are observing high solubilities, good values for the redox potential while maintaining low viscosities, and more importantly, the synthesis is quite straightforward. In this sense, we discarded the 2,2-bipyridinium salts because of their stability. In the case of the catholyte, still we have the two options, the tempo derivatives and the ferrocyanide. And in this sense, all the main limitation of the tempo derivatives is the synthesis, which is not straightforward and requires 4 to 6 steps. In the case of the ferrocyanide, the main limitation is the solubility of the compound, which can be somehow solved by using ammonium cations, and as well the redox potential, which is significantly lower to the nitrosyl radicals. At this step, then we decided to evaluate all those compounds in the part of the scale-up with the collaboration with COC, that is a company that is helping us on this process. So there are some things that we have to consider as the toxicity or the chemicals that we are using in the lab later for the upscaling, redefinition of the solvents and so on. The synthesis route that should be as efficient as possible, and that some operations can increase the cost when we go to pilot plant. That's why if we focus just in our case, we wanted to evaluate these 3 compounds that we mentioned. And in the case of the biologens, the synthesis is quite straightforward, and we can even isolate the product as a solid. So this is the reaction scheme that is depicted here, and this is the desired compound that we wanted to produce. In the case of this synthesis, we have to change the DMF, and it was replaced by an alternative high boiling point non-toxic solvent, as could be some alcohols or aromatics. It is quite important as well to define the efficiency of the reaction in terms of selectivity and yield, because we can also go into some side products, as could be the monoalkylated piperidine, and as well some side reactions coming from the ring opening of this propanosultone. This can be clearly observed here in the NMR. We have some extra signals in aromatics and as well in the part of the aliphatic side. So is this really important? Are those impurities really important? So we confirmed that yes. Here we have some data about the ohmic resistance of those compounds, in which, depending on the impurities that were present in the material, we have a significant increase in the resistance of the cell. However, COC managed to solve this in collaboration with us, and now they can produce this product with high purity with the same properties that we have at lab scale. So here, when turning into the part of tempo derivatives and ferrocyanide, the tempo was discarded because it requires a really long, quite long synthetic route with 4-6 steps, which at this level is making the cost of the electrolyte high, and it was including as well some purification techniques as chromatography. This does not mean that this compound is not good or valid. It means that we have to readapt the synthetic route to make it cheap or feasible. In the case of the ferrocyanide, this all was much more simple because there was already an existing industry for ferrocyanide production, straightforward. The synthesis is quite straightforward, and the main problem is just the water evaporation. So we came up with this solution in which we were using biologen with ferrocyanide at a cost with a competitive cost. So at this point that we have already defined the active material, we turn into the part of the electrolyte formulation. So this is kind of a new beginning, a new start point. Why? Because the active material is an important compound here in the electrolyte, but as well we have to consider other aspects as the pH, supporting electrolyte salts, charge carriers, and which is the effect of temperature, SOC, and operating conditions on those. So we can see clearly here in this graph in which we are depicting different compositions of the electrolyte by means of increasing the concentration of ammonium chloride going from 1 molar to 3 molar. We clearly observe in the part of the conductivity how this is increasing significantly. As well, we can compare here in those two rows is how the viscosity is increasing when going to the biologen with SOC 0% to SOC 100%. Apart from this, at this point, we fixed the concentration of the active material based on the solubility and how this is changing with the temperature. And as well, we define the pH as 7 and the charge carrier as ammonium chloride. So here we have depicted a charge-discharge profile of this compound, which seems to be quite stable. So apart from this, we have to focus on the optimization, continued optimization of this electrolyte, and see how this is affecting the thermal stability, conductivity and efficiency, and as well the crossover, especially water transport because of the ionic strength. But this is something that will be discussed later in another talk in this session. So just to summarize is that we managed to have good efficiencies for this system. So some remarks more than conclusions is that the development of electrolyte is a long way from chemistry selection and should be adapted throughout different stages. Once we get information about the information about the electrochemistry, once we get information about the upscaling and so on. In the case of the active materials, they define the electrochemistry, but there is much behind. We have to focus as well on the performance of the supporting electrolyte and how this will change the stability. For the scale-up process, this is a critical process. It has a critical role in our evaluation of materials and as well in the implementation of those. And it is really important for the irruption of new chemistries. So there is a bottleneck that we have to surpass when trying to go to new chemistries, because it is really tough at the beginning to manage to get data at a stack level, having enough material for this. So more scientific conclusion is that we managed to have a total of more than 20 active materials, and that we define 2 different electrolyte solutions. So as I mentioned, one of those would be with a high performance electrolyte with up to 1.3 volts, with a capacity decay lower than 0.01% per cycle, and based on highly soluble active materials that potentially can get to high energy density. In comparison, we have a cost-competitive solution based on biology and ferrocyanide, which has a lower cell voltage, but still a high capacity retention, and that with some tuning we managed to go for high energy efficiencies, which is really valuable for working at neutral pH. What is still to come is we have to successfully integrate those electrolytes at stack level to confirm the properties of those and see how they perform in a bigger scale. So thank you all for your time, and hoping for your questions.
So thank you for a nice and clear introduction to the chemistries and comparison of different chemistries. So now it's open for questions. So is there somebody? Yes.
Hi, thanks for the talk. So as I understood, it's a neutral flow battery, right?
Yep.
At pH 7. So have you measured the pH change on the ferrocyanide side? Have you seen any change of the pH on the ferrocyanide side?
In the case of the ferrocyanide, we don't see any change, or any change that we believe that is promoted by the reactions of the ferrocyanide, because this is not, so the protons are not involved in the redox equilibria of this species. What we may see is that in the case that we have some unbalancing of the reaction and some permeation of oxygen, you can see some changes in the anolyte, and that this can have an impact as well in the catholyte because of the compensation of the pH.
Okay. Mm-hmm. Yeah, thanks.
Thank you. Maybe a question also from first. Okay, I will quickly ask just what is actually the energy density of the electrolyte in your formulation in 1 hours per liter or per kilogram of electrolyte?
So the one that we define as a cost competitive one was around 9 watt-hours per liter. That's the one based on biology and ferrocyanide. But for the other ones is something that we are still to prove. So how far can we go? Because the solubility of the materials can go above 2 molar, up to almost 3 molar, but it's still to confirm if this is going to be stable when we work at this high concentration, especially considering that we have nitrogen radicals.
Hello, Edu. Thank you for your nice talk. In the synthesis of the sulfonate propyl biologen, this synthesis must be performed under argon atmosphere in order to avoid the opening of the sultone. If you are using an alcoholic solvent, this alcohol is not going to open the sultone.
Yeah, this is something that could be an option, and actually we got surprised with when COC was using this material, but in terms of later purification and removal of the solvent, it's much more easier to remove an alcohol than removing the DMF, for example. And what they were using, for example, you can always use a bulky alcohol that could not go into the substitution or reopening of the propanol-sultone to compensate this, for example. In the part of the using an argon atmosphere or not argon atmosphere, what we have seen is that it's not that critical in the lab. It depends as well on the storage of the propanol-sultone. So as far as the starting material is okay, it seems to be good. But we don't know how is this going to affect when we go to bigger scale. So maybe we can discuss later with Lubomir here.
Thank you. We will have also one question from the chat.
Yeah, hello. From Carlo Cancinello, he asked, have you tried to use ferrocyanide as a pozolyte with different biologen, not zwitterionic? And if yes, with which membrane? If you try this ferrocyanide with different biologen.
No, mainly the use of the ferrocyanide, we couple it with that biologen with a sulfate moiety, because this is the way that we make it compatible with cation exchange membranes, because of the ionic nature of the compound. And second question was the membrane that we were using. So maybe this is not the question for me, it would be the question for next talk that will be given by Ivan, in which Salmeron, in which we were using like different membranes from Fumatech and other companies, and he can develop a little bit more on this.
So Eduardo, thank you once more for the presentation and for clear answers to all the questions. And let me now invite a second speaker, who is Ivan Salmeron from Madrid, and he will talk about membranes. That means the issue that was also asked in the last question. So Ivan, the floor is yours and you can start. I hope that your presentation will start quickly.
So, hello, good morning, everyone. My name is Ivan Salmeron. I'm a PhD student at the Autonomous University of Madrid. And also with my colleague Juan Asenjo, which is also involved in this investigation performed at our institution, I'm going to talk about the membrane developments in the redox flow batteries within the project HIGREEW. So, first of all, an ion exchange membrane needs to fulfill the following characteristics. Needs to be stable in the media of operation, as well as having the best ion conductivity as possible to avoid high overpotentials of the cell. It must resist during long periods of time, so a mechanical strength is required, and as well as good perm selectivity to get high Coulombic efficiencies. And on the other hand, regular transfer of water. This is related with the difference of osmotic pressure between the tanks. So we need a balanced system to avoid undesired thermodynamical processes, such as the permeability of the active materials, which needs to be the lowest possible, and be competitive in terms of cost within the market. So we were required to evaluate different commercial materials, such as cationic and anionic ion exchange membranes and porous separators from companies such as Fumatech, Solvay, and Amersil. Depending on the active material, we will deal between cation or anion. And in case of porous separators, I have to say that they were considered, they were evaluated because they are cost effective and they possess very high ion conductivity, but the media pore size is extremely huge, so the permeation of the active species will be so dramatic, so they were difficult to work with, so they were discarded. And according to the rest of materials, some fundamental parameters were considered, such as the ion exchange capacity, the ability to absorb water of these materials, the resistivity, and the perm selectivity. So, the HIGREEW project, the targets of the HIGREEW project were considered taking into account the state of the art in vanadium redox flow batteries, and in concrete with the naphthalene type membranes, which is the most used. And here I put in this slide, if you can see the values of this table, they are quite optimistic, but I must say that some of them are some relevance, such as the cost, the conductivity, and voltage efficiency, which is related to the cross-mixing of the active species, related to the voltage efficiency losses. So we have made a kind of screen selection of different commercial membranes based on cost, conductivity, and permeability tests. So here in this slide, I show you the screen selection performed in case of anion exchange membranes, in which this graph I put the different anion exchange membranes that we possess in the Autonomous of Madrid, and I normalize the values to make the comparison easier. So as you can see, in terms of conductivity and the permeability, in this case with the B13 molecule of the HIGREEW, one of the molecules of the HIGREEW, and the cost, two promising candidates were selected as a promising materials feasible to our battery application, which were the AA3M50 and the FAA3PE30. Both membranes are from Fimatech company and are non-fluorinated, but the last one contains polyethylene as a reinforce in one of the faces to enhance the mechanical resistance. But I have to say that maybe the last material maybe is not so useful from the stack manufacturing point of view due to it's difficult to handle and it's too thin, just around 20 microns. In case of cation exchange membranes, the selection was performed in the same way, but it was a bit more difficult because we had to deal with more than 3 membranes, at least 6. So the promising candidates were the FS950 and E6C30, although we also consider the FS930 because it's the same material, but by its thinnest version. Both also are from Fimatech. The first one is perfluorinated and the other one is partially fluorinated, according to the composition of chemistries that we have seen in our infrared spectra. So these are the commercial materials that we have taken into consideration, but the cross-mixing, the crossover is a kind of transport phenomena that will be detrimental and we should avoid. So this is a problem that needs to be considered seriously and overcome. So in order to do so, we proposed different membrane modification strategies, which I'm going to explain. The first one is the in situ polymerization. It consists of filling the pores and the interstices of the pristine membrane with another polymer to reduce the pore size and blocking or hinder the diffusion of these active species between tanks. And I have to say that this methodology is quite simple to carry out, so easy to scale, and the chemicals involved are quite cheap, as well as the low toxicity of them. The other one is the layer by layer, which consists of adding different polyelectrolytes in one or both faces of the ion exchange membrane. It let us enhance the ion conductivity. However, the homogeneity of the process is compromised even more if we want to scale to larger pieces of area of membrane. And the other one is the incorporation of hydrophilic nanoparticles. In this process, we need to solve our commercial membrane and then make a colloidal suspension with such nanoparticles and then recast. This is an interesting procedure because it's also cheap, but requires membrane dissolution, and the chemicals involved in this procedure are not considered so green chemistry. And the critical step in this procedure is then the recast. So the last two methods are very interesting from the at lab scale, from the scientific point of view, but the ones to address to large scale, maybe the in situ polymerization is the best option and the one that we carried out. So at this moment, we have 2 alternative materials from each family, cationic and anionic. Here you have in the left of the slide in this table. And I collected some relevant data of these materials, such as the water uptake and solid ratio and ion exchange capacity, which are found values in a typical range of battery operational mode. And as well, we check as well the ion conductivity, being the cationic ones more conductive than the anionic ones. According to the HIGREEW guidelines, in scenario 1, we were dealing with the B13 molecule and temple molecule. And in these membranes, we were required to test how was the permeation of the active species in pristine membranes and its modified version. And as you can see in the graphs, in most of cases, the permeation when using or modification was successfully reduced. Such permeability tests were done in H diffusional cells with no current, but during 1 week of evaluation. Also, HIGREEW was dealing with another 2 different scenarios. The scenario 2, which is considering the B21 and C11 molecules, as you can see. And again, the modification proposed reduced in most of cases the permeation. And in the scenario 2, I have to say that based on the chemistry involved, we needed to use anion exchange membranes. Whereas in the scenario 3, according to the B22 and C31 molecules, the family membranes that were required to evaluate were cationic ones. And also, as you can see, the permeation rate was reduced when using the modification. I would like to point out that in the scenario 3, the permeability values, among further tests that we have performed, it was done in a redox flow cell with flow rate, with a certain flow rate and applying current, and during 1 month of evaluation, which is also important to foresee the lifetime of our membrane and battery prototype ultimately. So since HIGREEW guidelines or line is interested in the scenario 3, we wanted to perform some membrane evaluation according to the procedure suggested by University of West Bohemia by cycling the battery, and at a given electrolyte configurations at 900 millimolar of the active species in 1 molar of, in this case, in 1 molar of ammonium chloride, we evaluated which was the resistivity of our membranes, pristine and modified ones. Well, I have to remark that in our case, we were using a homemade glow box, so we have some oxygen permeation that we have to keep in mind, but to compare with our results, it's okay. So as we can see, when performing our modification, our membranes increase in resistivity, and this leads to lower voltage efficiencies then. And in case, when compared between the different cationic ones, we found that the E630K was the most resistivity, was the one with more resistance. So they were discarded, even the commercial one. But I have to say that despite of having more resistivity, the permeation of the active species was reduced. And also here in this slide, I collected some interesting data, which was provided by the University of West Bohemia, that I would like to comment and share with you. So first of all, I would like to point out that membrane is a sensitive material, and the different properties, and the different properties that you can find in these materials strongly depends on the electrolyte configuration, because these membranes swells and has a certain level of hydration, and depending on this level of hydration, the ion conductivity will be different and may differ. So in general trends, in diluted compositions, in compared to the concentrated ones, the resistivity was decreased, and this is because the membrane swells and the different osmotic pressures between the outside, the membrane, and the inside. So the membrane behavior will be different. So the data collected in this table was considering this electrolyte configuration as the other slide, which was 900 millimolar of the active species and ammonium chloride, but different concentrations of the supporting electrolyte, which is the ions that are supposed to exchange our membrane. And this, in this case, cationic, so the ammonium ions. So going into more detail with this data, what we can see is that upon cycling or membrane modified version, slightly recovers the ion conductivity, and this means that our membrane needs a small period of activation, and even more if the membrane is assembled in the dry state form. Yes, this is a fact that our modified membrane is more resistant than pristine one, but as I was talking about, depending on the electrolyte configuration, we have different behaviors. For example, in the diluted cases, we have a near 40–50% of increase in conductivity, whereas in the concentrated ones, we are dealing with near to the 90%. So this fact reinforces what I have aforementioned. And also having a look at the Coulombic efficiency or modified membrane apparently do not compromise the perm-selectivity. So the exchange of ions will be done as the pristine ones. Having a look at the voltage efficiencies, which is related to the energy density of our future battery prototype, we can observe some voltage efficiency losses. But which is very interesting is that in the diluted configuration, the voltage loss is near 20% as well as in the concentrated ones. So we have near 40–50% increase in conductivity, whereas in the other side, near 90%, but the same voltage efficiency loss. So this is an indication that maybe the resistivity of the membrane is not the only parameter we have to focus on. There are something else. So, but what about, so I would like to say that this data is considering 50 cycles. So let us wonder what will happen to 1,000 cycles or 1 month of operation of the battery, no? Because this fact let us wonder if we should ignore further losses in long-term battery cycling tests, because maybe modified membranes could help us in that situation, because the crossover is something that we will have to face at, in a certain time. So it needs to be analyzed at long-term experiments, and very important, even if we want to compare the different membranes with a very well-defined electrolyte configuration. If you have different situations, the comparison is much more difficult. Just a brief conclusion. We were inquired to foresee strategy or feasible strategy to overcome the problematic of the cross-mixing of the active species. And according to our permeability test, we successfully reduced in most of cases our permeation rates. We have made a kind of a screen selection of different materials considering very important parameters such as cost, conductivity, and so on. And also I would like to remark and to say that when performing our modification in our materials, we have made some tensile strength analysis, and we observed that our modification enhances the mechanical strength as well as the flexibility of our membrane, which is something interesting from the stack manufacturing point of view, because we are extending the lifetime of our membrane material. And this is something we have recently published, as you can see. And
so, Ivan, thank you for the presentation.
Okay.
Because I want to allow some time also for the discussion.
Okay.
So, first of all, most of the discussion will probably proceed in the coffee and electrolyte break. I will just give you one quick question. In the first presentation, we learned that the pH of the electrolyte can change during charging, discharging. Is the pH going to have some significant effect on the, let's say, permeation or crossover over the membrane?
If we have some pH variation upon cycling test, we are changing the different concentrations of the one tank to the other one. So, in principle, if the active species, we reduce the permeation of a kind of exclusion size. So what will affect more detrimental in this case in membranes will be due to the perm selectivity, because this is a cationic version. So if we go to the more higher pH systems, a cationic one is not, it doesn't make sense, because we will need to deal with anionic version.
So thank you for the explanation, and once more thank you for the presentation.
Thanks.
And now let me invite a third speaker of today, who is Matthew Etienne from CNRS, and he will present a talk on electrodes. So I will ask technical assistants to help with the presentation.
Oops.
Yes, it's coming. So Matthew, the floor is yours.
Hello, everyone.
Once everything is set up.
Hello, everyone. So I will be talking about electrode materials. So first, I want to thank my colleague who have been performing the work. So the objective of this work package, of this task in the project, is to reach a certain range of reactivity, 10 to minus 3 centimeter per second for the kinetic of electron transfer. So this is a electron transfer reaction, is a basic reaction that allows to transfer electron with the electrolyte in the solution. So it's a critical reaction, because if we have low kinetic, we are losing some of the energy during the charge and the discharge. So the first objective is to reach this 10 to minus 3 centimeter per second, and the second objective is to reach a certain cost, less than 100 euro per square meter of the material. So before to reach this range, we need to measure accurately this kinetic, and this is where we started to work in this project by looking at the electrochemical measurement at the micro scale, at the microfiber scale, and just at the local scale at the end. And I will tell you why it is important. So first, the first natural way of working is to start with the graphite felt. So it's a porous electrode. We have here some representation. It is composed of fiber. This is a material we decided to use in HIGREEW. And so this is a priori, it is the best way to start measuring the electrochemical activity with this micro scale range. So this is a typical cell we use, some working electrode, and then some counter electrode in order to have a good distribution of current. And this is one first result we got. So we are not very concentrated solution. We have two materials, that is non-activated and activated. We have here two typical electrolytes we use during the HIGREEW. We tested all electrolytes that were provided by the partner. I just use one example. You have the tempo-based molecule and ammonium hexacyanoferrite. And what you can see here, so you see a difference between activated and non-activated, but it is essentially what we call the capacitive current. And regarding the activity, so we have oxidation reduction peak. Regarding the activity, when we look at this cyclothermogram, this experiment, we don't see much differences. So this could be a good news. It means that any material provided by the provider, commercial provider, will be very good for this reaction. Is it true? So we went further, so we can analyze this kinetic with some model given in the literature. And the kinetic that is extracted here, in this condition, perhaps not perfect, but it is very high kinetic, higher than 10 to the minus 2 centimeter per second. So 10 times higher than the target we have in HIGREEW. So this is great. So we have this is a good news. We reached the target from the beginning of the project, I would say. We went further. We implemented electrochemical impedance spectroscopy, similar condition. I do not go into the detail of the experiment because I'm not the expert, I would confess. And we analyze this electrochemical impedance spectroscopy with some macro homogeneous model that allows to extract different parameters. And the parameter we are especially interested in is this heterogeneous charge transfer kinetic constant. So there is a lot of parameters. So for sure, we will have a good fitting, a good agreement between the experiment data and one version of this optimal parameter, because there is many parameters. So it's not so easy to fit. But at the end, we can get this kind of value. So non-activated material, activated, and for tempo base and ammonium hexacyanopherate. And non-activated material for tempo, for example, is around 10 to the minus 3 centimeter per second. And activated one is a bit less, a bit more than 10 to the minus 2 centimeter per second. So great, again. Similar result, I would say, with the hexacyanopherate, the second electrolyte. We see a difference between activated and inactivated, and we reach somehow the target we were looking for, 10 to the minus 3 centimeter per second. But let's go further. So this is complex model. We have to use diluted solution also for the analysis, which is not perfect when we consider the application, that is concentrated electrolyte. And one other option, so we can do it with graphite felt. It's more difficult to do with carbon paper or some other form of material, but with graphite felt, we can easily do this experiment. This is reported already in the literature. We have the graphite felt, it is some fiber, and we can extract one fiber. So we don't do it once, we do it several times in order to do a little bit of statistic on the analysis. And here we have the fiber, and we simplify the electrode. So when we have a porous electrode, there is different phenomenon interplaying, the reactivity, the mass transfer. And when we have a single fiber, so it's more simple experiment. We simplify the analysis. Of course, at the end, what is important is to know the activity of the graphite felt, but this allows us to really finely tune the analysis in order to be sure that we reach the target of the HIGREEW project. So here is how it looks like. So again, it is cyclic voltammetry. I do not enter too much into the details, the voltage, the current. What is important now is that we can clearly differentiate the activated versus the non-activated here for the hexacyanopherate, one of the electrolytes we use in HIGREEW. This is a non-activated, this is the activated. The displacement of this curve towards the left is an indication that the kinetic is increased. And this is the case for the two electrolytes that are tested here. And so we do the analysis, and now we have this kinetic analysis. So the value we get is slightly different. So we think that this model, this way is more accurate, but the kinetic value we get compared to the macro scale with macro fiber scale is a little bit different. So we were wondering, is it accurate? Huh? We get number, is it a good number or not? So just tempo, we are in the range of 10 to the minus 4. After activation, we reach this range of 10 to the minus 3, the target of HIGREEW. Then here for the hexacyanopherate, we are much lower. Before activation, we have 10 to the minus 5 centimeter per second, and we improve significantly by activation. So activation of the electrode is useful. So in order to check the accuracy of the measurement, we completed the measurement with electrochemical impedance spectroscopy. Again, I am not expert in this method. This is my colleague. And we do the analysis also with a model that is described in the literature recently, a PhD student in Australia, and we get a fairly similar value as in the previous table. So we are confident that this microfiber, it is more simple geometry, and this allows a more accurate analysis. So this is great. It means that now we have a method that is more accurate in order to screen the material and to see the effect we want to study in this HIGREEW project. One more comment. This is a short conclusion in this first part. So we could determine the kinetic value. This was one target of the project. On microfiber, it is systematically higher kinetic compared to the macro scale. So we have a difference. We suppose that the difference comes from this complexity of the macro scale measurement. And for us, the microfiber scale was just better. I just mentioned, so microfiber from felt can be extracted. We take the fibers and if we are good experimentally, we can glue and we do the measurement accurately. Another way we developed, it's one potential innovation linked to HIGREEW, is a technique derived from scanning electrochemical microscopy in order to contact the material without destruction. And so we do local measurement. This could be a good tool for quality control of the material, or for graphite. I'm not sure it's useful, but for carbon paper, for some other material. So this is just one potential innovation that is coming from the project. So now we have a good method for activation. We tested a quite high range of, we tested different activation protocol. So some thermal activation under CO2, under air. We do some activation in solution. We do some activation reported in the literature using urea in order to introduce some heteroatom. And here is some illustration of this activation. So we have the non-activated material. When it is on the right, it is low reactivity. And when we do the activation for a certain time, we move this electrochemical reaction to the lower potential, and we increase the kinetic. And the same here for another example. And we reach, with the best activation we tested, we reach an activity that is higher than observed on the commercial activation. So this is one result of HIGREEW. What we have to be aware, what we need to take care is the stability of the activation. This is an example. Because the measurement we do is very accurate, probably we could not see this degradation at the macro scale, but at the microfiber scale, we can see that here is a before activation. We activate, and with time, the signal is going back to the right, to the less active situation. So we have to be aware that after activation, the material is slowly deactivating, and we have to pay attention to that, so that the activation protocol we are choosing is the most stable with time before implementation in the battery. And one more notice is that this measurement can also be used for following the the stability of the electrochemical reaction. This is an example we measured recently, where we are cycling with the microfibers in an electrolyte with halogen. And depending on the condition of the cycling, we see that there is a degradation of the electrochemical signal. So we know that the long-term stability is important. So the loss of stability of the battery can come from the electrolyte. But in some condition, if the potential is not well controlled, there could be some irreversible modification of the activity. Here we lost completely the activity, but we use some conditions that should not be present in the battery operation. Yeah. So I come to the conclusion. We could perform quantitative kinetic analysis on graphite felt material. So you see, we try different approaches in order to be accurate. This quantitative assessment is important because this allows us to conclude clearly what are the best treatment for the HIGREEW electrolyte. And we identify this material. So some commercial material we have tested. So we have tested material from different providers, from SGL, from Avcar, from Zoltec. So all material has their advantages, and we were quite happy with. At some point on the project, we focused on SGL for practical reasons, but I think some other material could have been also used for the optimization. And we could identify, especially with urea treatment, some condition where the kinetic of the electron transfer were improved compared to the commercial material. And so the microscale measurement, we think, with the microfiber or power with this scanning electrochemical techniques we started to evaluate, could give a good opportunity to evaluate aging degradation of the electrode. Thank you for your attention.
So thank you, Matteo, for the presentation. We have enough time for questions. Maybe we will start with a question from the chat. So maybe Jirka will.
Hello, Adam Whitehead asked, how were the fibers stored between measurements during the degradation studies?
So I don't understand.
How were the fibers stored between the measurements during the degradation studies?
How?
How were the fibers, these carbon fibers stored between the measurements?
So what was the environment of the fibers in between the measurements?
For the degradation. Yeah. So it was for the long-term degradation. Yeah. So it was not. We did not pay attention to the environment at that time. We were just storing in the lab. So it could be that it is some chemical adsorbed on the surface, but we did not go further. But we noticed that there was a clear effect of aging of the electrode on the kinetic. We did not pay attention on the environment. We did not keep under nitrogen, for example. Yeah. We did not pay attention. So this is a degradation on the bench, on the lab.
Yeah, he's Peter. So I'm very happy that you take a more controlled electrode, because a felt is a very bad electrode for CV, because you have different diffusion regimes in the felt, porous diffusion, so you cannot really judge CVs from felt. It's really difficult, you can't do it. So in your microelectrode you have definitely more control over the experiment and can get really data out of, and you can also define surfaces, which allows you more information. The question I asked, did you already do a further kinetic analysis so that you exclude that, for example, adsorption on the electrode makes you the good kinetics?
So I'm sorry, because the sound, I have some problem with ear. So did I do some
further kinetic analysis, like taking
so
different scan rates?
We do compare for the microfiber. We do the analysis, the kinetic, with cyclic voltammetry and with impedance, yes. And we get exactly the same data. Mm-hmm. So perhaps this is replying your question. So further.
The question was, how do you? Did you make a further kinetic analysis about follow-up reaction of the, so that you can exclude that it's an absorption on the electrode, the good kinetics?
Yeah, we can discuss perhaps a little bit later. Yeah. So when we conclude about this discrepancy between macrofiber and the macroscale and macrofiber, we do not conclude that necessarily the macroscale is so bad. But so we still keep option that there is still an error in one of the measurements we do. You know what I mean? We think that the more accurate is the macrofiber because it's more sensitive. So it is a tool we need to use in this project to optimize. For sure. Then regarding the mechanism, yeah, there could be some adsorption, for example, for the stability on the viologen. When we go very low, we see some irreversible change. So there is something depositing on the surface. You see, but on the other experiment, we did not see such a phenomenon, adsorption. This is, if it is the meaning of your question.
So thank you, Mathieu, and we will then continue coffee break. Next question.
Yes, hello. This is Peter Klusner from Shell. I have a question about the degradation that you showed of the electrode material. How do you distinguish between the degradation of your electrolyte versus that of the electrode?
No, because in this specific experiment, so the measurement was done in one electrolyte, and it was Ranin, a postdoc, doing the work. Then she changed the solution, and then she do a new measurement. So we are sure that it is not the solution is fine, and then it's a microfiber. The microfiber will not change the total volume of your electrolyte. You know, it's not possible. So, but she changed the solution, and we are sure that this is only the electrode that has changed. Yeah, this is important.
So maybe a final question also from me. Of course, we are concerned with the decay of electrolyte. It's quite small per one cycle, as we learned during the first talk today. And is this decay going on like in the bulk of electrolyte or at your electrodes? And have you studied the effect of activation on really the small decay of the electrolyte of organic chemicals?
Yeah, we started to do with Peter some studies, so we don't have yet a conclusion. But this is one objective now for the HIGREW, is to study this slow degradation and to identify if the electrode is contributing.
Mm-hmm. So thank you once more for clear answers. And let me now invite the next speaker, who is Václav Čmolík from University of West Bohemia in Pilsen, who will talk on the optimization of entire cell. That means putting the electrolyte, the membrane, the electrode, and the technology together, and doing the optimization still on the laboratory scale.
Thank you very much, dear Chairman, ladies and gentlemen. I want to show you my presentation in which I want to tell you what is possible to do with redox flow battery when all internal components such as membrane, felt, or electrolyte are determined. Few words about me. I am part of a group of engineering of electrochemical processes. We are working in New Technologies Research Center, and we all belongs to a bigger family, which is named University of West Bohemia. It's not a secret information that we have a strong bond to Pinflow company. My colleagues are interested in some other scale-up problems, for example, zinc-iron battery, but I will talk to you about HIGREEW project today. So you already know the story, how we got ourselves to this initial compartment. For the studying, we used the commercial available lab cell from Pinflow company. It was necessary with this chemistry to use inert gas. And on this slide, I want to show you some directions of flow. And I want to mention that, for example, outlet of the cell is always up because we want to remove all bubbles from the cell. So how it looks like. We have membrane, which is held by two seals. Here are two felts, flow frame, another seal, which is necessary, carbon polymer composite, and a copper collector. Everything is held by 8 screws between two end plates. So decision was made that best molar concentration of organic compound and inorganic compound is 0.9. And question for me was to get the best combination of supporting electrolyte concentration on both sides to get the best characteristics of redox flow battery. Unfortunately, we had to little bit decrease the maximum voltage of cell because of secondary reaction of organic compounds. This product is much worse soluble in our aqueous environment. So maximum voltage in our cycling procedure was only 1.15 volt. You know the story, so the target was clear. Cation exchange membrane, two main compounds, but different ionic strength. So we know that the water molecules will transfer from one side to the second, and we want to decrease this effect by adding some amount of supporting electrolyte. We want to find optimal temperature. We have to find ideal flow rate. All of these characteristics for get highest voltage efficiency, lowest resistance, and also I want to show you how predictable behavior is still important for the industry scale. On this slide, I want to show you the effect of temperature on the cell. We started with the smallest cell, and we chose the molar concentration of 2 moles per liter on the organic side and 1 mole per liter on the inorganic side. Flow rate was set up by 20 milliliters per minute. Voltage was mentioned, and the tested temperature was from 20 to 40 degrees. You can see more than 20% in voltage efficiency, and mainly more than 20% in initial capacity loss. So from this data, we get that might be useful to raise the temperature for another experiment. Another data from smallest cell, these are combination of concentration of supporting electrolyte, and the data were almost the same. So bigger temperature means bigger capacity and better values at voltage efficiency. Before the experiments on the large cell, we have to find the best flow rate. And on this graph, you can see decrease of inner resistance of the cell with given temperature and given temperature and range flow rate. We found that 80 milliliters per minute is not good due to some pressure and energy losses. So we want to test it another experiments with flow rate of 40 milliliters per minute. Let's go to bigger cell. These are some resistance characteristics, what we get. We also try to find another combinations of supporting electrolyte to ensure that we are going to right way. And from this data is clear that the minimum of resistance of this chemistry is when we use 2 moles per liter on the organic side and 0 concentration of supporting electrolyte on the inorganic side. But if we cycle the battery at the higher temperature, the best combination of supporting electrolyte concentrations is 3.0. From this data, it corresponds to some cycling performance like voltage efficiency and initial capacity loss. It means that system with lowest resistance has the best voltage efficiency at given temperature. But if we go higher with temperature, the system 3.0 wins, as I mentioned earlier. If I was talking about some predictable behavior, you can see that if we cycled the battery with different concentration of supporting electrolyte, we get these graphs. And from the first graph, you can see that after 50 cycles, only 50 cycles, we get a gap in capacity, which is equal almost 50%, 60. If we goes with temperature higher, then we get more than 200 milliamperes per hour, and the behavior of these electrolytes are much more predictable. So it means that if we go higher with temperature, battery is less independent on the amount of supporting electrolyte concentrations on both sides. But what was our goal? To moderate the overflow. So you can see after 50 cycles that overflow is here as a percentage of initial volume, and the upper one is the organic side and the lower one is the inorganic side. From this graph, you can see that overflow is temperature dependent. And we also try to find best conditions. So maybe if we will be cycled only 50 cycles, battery with 2-0 combination at temperature 30 degrees, maybe we will got overflow equal to 0, but there is another problem. If we do more cycles than 50, overflow is turned to the other side. I think it is caused by membrane, and if we want to do better, if we want to get better values, we should focus on the membrane and get the better piece between each half cells. So if I can do some conclusions, we found the optimal flow rate with respect to resistance and pressure and energy losses. And with higher temperature, we found that the system has lesser initial capacity loss, a higher voltage efficiency, lesser resistance, and lesser dependence on concentration of supporting electrolyte. So if we want to cycle this battery at 20 degrees, the best combination of supporting electrolyte combination is 2-0. But if we want to get the temperature higher, it looks like that the 3-0 combination is the best. Thank you for your attention.
So Václav, again, thank you for the presentation. Again, we have enough time for questions. Is there? No, there is no one from the chat, so we will start here.
Yes, hello. Thank you. Very nice presentation. I have a question about the capacity of your electrolyte. You showed the difference of temperatures. I was wondering what is the ratio of the effective capacity compared to what is the theoretical capacity? I could not make the calculations myself so quickly.
Ratio of effective capacity.
Yeah, so what is the theoretical capacity of your electrolyte?
Yeah, it is a little bit more than 1000 milliamperes per hour if we use 50 milliliters of electrolytes.
So you use about 50% of 30 to 50% of the effective?
Yeah, at the 20 degrees.
Okay, thank you.
Okay, there was a next question in the back.
Thank you for the talk. This is a remark to your presentation, but also to previous presentation in the morning. I think it makes sense to always put the current density when you're talking about the voltage efficiency. So that strongly depends if you're running at 10 milliamps per square centimeter, 50 or 200. You can crash any voltage efficiency if you're going to very high current densities, which is, on the other hand, needed. If you want a good commercial product, you need to have a high current density. So I would recommend to always give this information on the slides when you're talking about voltage efficiency. So maybe it is somewhere in the earlier slides and I missed it, but it's helpful for the reader to see always the current density.
Yeah, it wasn't there in this presentation, and it was 100 milliamperes.
Okay, so that's a good, reasonable, thank you.
Yeah.
Yeah.
Okay, maybe I will also ask some questions. The first one will be, what was quite significant effect was the increase of temperature from 20 to 40 degrees, and you managed to improve the voltage efficiency about 12% and to reduce the capacity loss significantly. What exactly is the mechanism for such a strong improvement with temperature? What exactly is going on? Is like a better conductivity, less resistance, or some differences in kinetics? Do you have already some idea, hypothesis, what is the real underlying explanation of it? Not just the observation.
With high temperature, we have low viscosity, and I think it has an effect for the system resistance.
Okay, that means that you believe that just a system resistance can improve the voltage efficiency, but also what about the capacity loss? That's probably not associated just with the viscosity, that the capacity loss also reduced significantly.
Yeah, I don't have an answer for this question.
Okay, so we will discuss this in the coffee break, and we will
thank you.
open it. And another question, in the beginning you mentioned that it's quite critical to perform your experiment in inert environment. That means probably nitrogen gas. Why exactly? What would be the effect without a nitrogen? That means in case we allow air to be in contact with the electrolyte. Would it be some capacity decay, and how fast the capacity decay would be in contact with air?
Yeah, I don't know the kinetics, but we want to avoid oxidation of organic compound.
Okay, it will go, and how fast this oxidation is going to be, like per cycling or per hour, or do you have, of course it would depend on the geometry, on the solution and so on, but do you have some data how quick this oxidation degradation was of the electrolyte?
Me not, maybe my colleagues, I don't know.
Okay, maybe it will be addressed in some of the next talks. So once more, thank you for your presentation.
Thank you very much.
And now let me invite the next speaker from the PinFlow company, who is Jirka Hrvat, and he will talk now about the design of the hardware. That means still a small cell or small stack for the organic redox flow battery, and the experience he obtained in this area. So we will wait for the presentation to start, and once the presentation is there.
Okay, hello. My talk will be about cell design and how to optimize the cell design. But at first, I will talk briefly about PinFlow company. So in PinFlow company, we do continuous screening of the material. We continuously develop our stacks and improve the performance of the stack. We are also active in 2 Horizons projects. We also manufacture and sell vanadium redox flow battery labware, and also we got some first pilot installation of redox flow battery in Czech Republic. So from this redox flow battery labware, we sell labware from very small stacks and till very high testing pilot benches and very large cells. In the chat, there was the Keith Stevenson mentioned that it's very good that University of Bohemia gets some testing protocol, but it would be good to get this protocol for a whole community. So I absolutely agree with him, and I think that a very good first step would be to use these very nice cells for this protocol. Okay, now let's come back to more scientific topic. So if you are something like, if you do some basic research, you are scientist in the lab, you want to get the best performance of your cell. So you can often see in the articles that there is active area of the cell like 1 centimeter square, and the flow rate is, let's say, 20 milliamps per minute. So it's something absolutely huge. And you think, okay, it's great, I get great performance as well. My flow distribution with very high flow rate is very, very good. So everything is great. But then you think a little bit more, and you think, okay, maybe the pressure drop with very high flow rate wouldn't be that great, and I will pay very much for this pumping power. So how could I decrease this pumping power? Okay, I will do my guide channels and so on very short, and thus the pumping power will be lower. But then you think a little bit more, as there are shunt currents, and you think, okay, when my guide channels are short, then the shunt current will be very high. So we need to find some optimum for this. Maybe to briefly explain what are the shunt currents. When you get a cell which is connected in series, and the electrolyte is brings in parallel, there is for current two pathways in which they might flow. The first, the desired one, is through the cell where the current is used for electrochemical reactions. But there is also another path through the manifolds, as the electrolyte is electrically conductive. So the current can also bypass the cell, and this current is not used for the reaction, and thus it's lowering Coulombic efficiency. So for proper cell design, we developed two models which might help us to optimize our cell. The first model, the analytical one, is computationally very, very cheap. And with this model, we are able to predict the pressure losses in our cell, and we are able to estimate the shunt current losses. The other model is CFD model, and with this CFD model, we are able to do further optimization with preliminary optimized geometry from this analytical model. To briefly explain our model, first the analytical one. The first part is about shunt currents. So on the right side of the screen, you can see equivalent circuit for our batteries. As you can see, the single cell is represented as a resistor in series connected with the ideal voltage source, and the electrolyte channels are represented as resistors. So we can estimate the flow of shunt currents when for this equivalent circuit we solute Kirchhoff's law, and we get the flow of shunt currents. For estimation of pressure losses, the cell was divided into three parts: the manifolds, the guide channels, and the felt. For estimation of pressure losses in the guide channels and the manifolds, the Bernoulli equation was used. And for estimation of pressure losses in the felt electrode, the Darcy's law was used. Okay, now briefly about CFD model. For CFD model, the Navier-Stokes equations for laminar isothermal flow were used, and we do a lot of optimization of the mesh for the computation. But again, this is used only for the guide channels and manifolds, because it's very hard to do CFD in the felt electrode. So the felt electrode was replaced with porous zone with some parameters, and so. Okay, we also validate our data by experimental measurements. Here you can see a scheme of our experimental measurements of pressure losses. For measurement of pressure losses, it was very simple. We just charge the electrolyte to required state of charge. We temper it. We set desired flow rate, and we measure the pressure before and after the cell, and from the difference of these two values, we get a pressure difference on the cell. So we do this optimization in 3 different sizes. So here you can see this active area of 3 cells in which we use our models. So the first results are for the small cell, and the geometry of the cell is on the right side of the screen. You can see that absolutely, let's say 99% of the pressure drop is in the felt electrode and not in the guide channels. So with optimization of guide channels in the geometry, we won't be able to decrease the pressure loss to pressure drop. What is positive if we get a very high pressure drop in the felt electrode is we get very homogeneous flow distribution. You can see that for both very high flow rate and very low flow rate, the distribution of the flow is very, very good. In the felt, there is only some small inhomogeneity on the inlet, but after that it's absolutely homogeneous. So this is good that the flow distribution is also good. There are results for larger cell. Again, the geometry is on the right side of the screen. You can see very good agreement between the model data and experimental data. But again, in this cell, the absolute majority of the pressure losses is in the felt electrode. And again, you can see that due to this very high pressure drop in the felt electrode, the flow distribution is also very good. But this design won't be probably very good, as you can see that the gate channels are very short, and thus the shunt current would be very high. I will talk about it a little bit later. The last experiment was for the, let's call it preliminary optimized cell design. You can see that here we got some small discrepancy between the model data and experimental data. Experimental data are a little bit higher. We are now quite not sure why is it. It might be because of inhomogeneity of felt material, or it might be caused that we wrongly estimated our local resistance coefficient for our analytical model. We will now currently the CFD model is being calculated, and after we get the results from CFD model, we will know where is the difference, because from CFD model we will be able to distinguish where is the problem. And so, as I told, that for the cell design of B, the shunt current losses would be probably very high. So there is a comparison of the cell B and this preliminary optimized cell C. Again, the cell designs are on the right side of the screen. And you can see that for both cells, the pressure losses are approximately the same, but the shunt current losses for cell B are much, much higher. So it's clear that in real, that the cell C would be much, much better for usage. Okay, to conclude my presentation, we developed 2 models. One very computational cheap analytical model with which we are able to, with very, very short time, preliminary optimized our cell design. Then after we develop CFD model, and with this CFD model, we are able to then further optimize our cell design, which is preliminary optimized from analytical models. And from these models, we do several computations, and we preliminary optimize first cell. And I would mention also that for organic redox-flow batteries, the optimization might be even more crucial than for vanadium redox-flow batteries. As in vanadium redox-flow battery, there is vanadium electrolyte on the both sides, and the parameters of the electrolyte are slightly different, but not that much. But in case of organic redox-flow batteries, as there are completely different electrolytes on both sides, the electrolyte properties might be completely different, and thus even a different flow design might be needed for both house cells. So thank you for your attention.
So thank you for the presentation, and the paper or the presentation is now open for questions or discussions. Maybe I can start. In the previous talk, we learned about the importance of temperature. in the stack, let's say, when you have 40 cells, how homogeneous is going to be a temperature field, let's say this 40 degrees, and how is it going to affect the flow rate distribution from cell to cell? So is there going to be some effect about and the temperature homogeneity in the stack, let's say?
Sure, it might affect it, but it would mainly affect the pressure drop, as the viscosity is strongly affected by the temperature. Then the viscosity would be affected and the pressure losses. But luckily, with increasing viscosity, the pressure drop is decreasing. So everything what is not used for 100% effective stack is used for heating, and thus we will at least something got.
Mm-hmm. Thank you. Maybe another question from me before somebody else will ask. Maybe in the beginning, initially, it's probably good to suggest some protocols for testing of single cells and stacks. Is there already some proposal or some for this protocol of the testing so that different studies would be comparable in terms of the numbers, geometries, and so on?
I think that there is still no community protocol, but maybe someone could say that I'm not true.
But if it's not there, would you propose one?
Well, you could. Not right now, but I believe that we all could discuss it later. What would be the best protocol for testing?
Mm-hmm. Sure. I'm not sure whether there was a question from the audience, from Peter. No. So in case if we don't have other questions, then we thank you once more for your presentation. And now we are going to have a coffee break, and the coffee break will end at 11:05. And sharp at 11:05, we will continue with the next talk. So, good morning, everybody. Let me continue with the morning session. And we have another 4 talks scheduled for organic redox flow batteries. And the first talk after the coffee break is actually online presentation. It's a presentation by the CTech company, and John Collins will give us the presentation.
Right. I want to give a little bit of a sort of a high-level talk on the scale-up work from sort of lab to stack within the HIGREEW project. I want to give a little bit of an introduction maybe to CTech and where we sort of sit with redox flow batteries. Then make some comments around sort of organic versus inorganic redox flow batteries. Talk a little bit about maybe potential cost savings connected with stacks where there's potential opportunities maybe with organic redox flow batteries. Talk a little bit about generic scale-up steps from lab to stack, and then talk a little bit about what we're doing within HIGREEW. So a little bit about the sort of original ambition, our initial approach within the project, and then a little bit around our current approach as to where we are now and going forward. So in terms of CTech, we're a sort of technology development company based in the northwest of England. We originally came out of a research centre for the electricity industry in the UK, which had a lot of background around electrochemical engineering. And the areas we tend to work in now are electrochemical and process engineering. And we're also doing a lot of work around nuclear decontamination. And we tend to make bespoke and standard sort of products from sort of lab scale up to pilot plant, with a few pictures of a few bits of lab scale sort of kit that we've sort of produced. In terms of sort of electrochemistry, we've done most things really in terms of synthesis, recycling, hydrometallurgy, quite a bit of work with ionic liquids, and including aluminium plating systems. The picture you can see on the right bottom there is a sort of 200-litre ionic liquid plating system in a glove box with 4 automated transfer that was successfully operating for aluminium plating. We done, as I say, we did quite a lot of work in the area of applying electrochemistry to nuclear infrastructure decontamination. In terms of flow batteries, we've done various design and builds of cells, stack, balance of plants and control. We're doing a lot of work in production of vanadium electrolyte systems for that. And we've got, in terms of actually operating and designing batteries, we've got experience around soluble lead, vanadium, zinc air, and a bit around sort of zinc nickels and cerium, which is what we're looking to do. We're looking to sort of apply that with the other partners within HIGREEW. I mentioned vanadium electrolyte manufacturer. So we've developed a process to produce electrolyte which just requires vanadium oxides, sulfuric acid, and electrons with no additional chemicals required to produce very high purity electrolyte at very, very low costs due to the inherent cheapness of electrons compared with chemicals. So we design plants and provide generally the electrochemical portion of the plant. You can see the picture there of I think that one's currently in sort of an 8 million cubic litres a year plant that's being built in South Africa with room for doubling the capacity on the side. And we're talking to a number of, we've got several other installations currently under sort of development. So returning more to the HIGREEW sort of topic. I was trying to think was what I could sort of say here that you all didn't really already know. So I was just I thought, well, I'd make a few comments really. As far as I could see, you know, the requirements for making a flow battery stack for an organic redox flow battery, as far as I'm concerned, are identical to an organic redox flow battery. You're trying to do the same things. You're trying to get a low cell resistance, high power density, low losses, low parasitic losses, and you ideally want to be on a route towards a low manufacturing cost. And you're going to be using pretty much the same building blocks that are in there. Unit cells in series, separated with bipolar plates, you know, with each unit cell composed of electrodes separated by sort of ion exchange membranes. And if you're dealing with systems that are all in solution, you know, without phase changes here, you're probably going to be dealing with three-dimensional electrodes, of which the most common type and most likely type, due to the stability and availability, is going to be sort of carbon felts and maybe carbon papers in here. And as far as I've seen, the design and manufacture, it's not particularly different between the two. Between the flow batteries, it's going to come down to the specific physical and chemical and electrochemical properties, rather than it being organic versus inorganic. That being said, based on what we've seen so far within HIGREEW, the comments I make about where we potentially see the difference between what we've done before is that the electrolytes appear to be a little bit more viscous, maybe. So we're looking at maybe increased pumping losses with higher stack pressures, maybe being a little bit more difficult to get up to the sort of limiting currents and things that you need, and it's got some mass transport limitations there, which could start to limit the sort of operating rate, the charge and discharge range that you can operate the electrolyte over, and the amount of energy that you're going to have to put into to do that. We've also seen a much bigger difference than we're used to in the properties between the pozolite and the megalite, which gives us some issues in stack design. As you know, if you run them at the same flow rate, you can have an inherent pressure difference across them, which could rapidly become a little bit too much for the membrane.
I'm sorry, John. Can you just go closer to your microphone? maybe it will sound be better. Thank you.
Yeah. So I was saying that may well cause you some issues due to inherent producing pressure differences across the membrane, which may cause damage, or if you're going to try and engineer around that, a number of different strategies, you may well have to pump one side faster than the other. You're going to get with that. You're going to end up with extra parasitic losses that way. You could maybe try and manipulate the flow, the permeability of the different sides. But then again, you've got to ensure that you end up with the same sort of compression, or you've both got to be compressed adequately on the different sides and have the right sort of kinetics. So it introduces an extra difficulty, which is enough to make things a little bit challenging. Certainly in what we've been looking at so far. We're also seeing bigger changes in electrolyte properties during use. That's perhaps maybe crossover and degradation. And that then prompts the question of what do you sort of design the stack to? Do you design the stack? Do you design the stack to when it's new, when it's after 30 days old or 60 days old, and that causes some issues there. So those three things I've mentioned so far have generally been perhaps downsides of things that make it more difficult. One potential upside is that the perhaps generally lower corrosivity, perhaps organic electrolytes, which allows a wider range of materials to be used, which could give you maybe cheaper manufacturing, better performance in a system. So I'll say a little bit more around that. So certainly in terms of the testing that we've done so far, we can see that we've seen very little degradation on a wide range of elastomer materials, going out to sort of like natural rubbers and silicones and nitrile rubbers and things that we have seen almost no change, and it gives us a lot of perhaps confidence in terms of we can go away from some of the difficulties of working with perhaps traditional elastomer materials like EPDM and Viton, and it's offering you cheaper solutions as well. It also opens up a wider range of sort of stack cell frame materials that could be used that might allow you to go with more confidence away from polypropylene into some materials that have elastomeric properties. For example, sort of thermoplastic elastomers and things which allow incorporation of sort of seals and assembly features into the cell frames during injection molding, which potentially reduces the number of components required and can simplify assembly, disassembly. Maybe allows you to use cheaper materials, less chemically stable and more cheaper materials, particularly maybe membranes there. One other possibility is you've got more options to potentially consider the use of metallic bipolar plates, which I think should offer longer term lower manufacturing costs, reduce thickness, weight, and ease of forming sort of flow distribution channels if you need to, just by a sort of a hydroforming process. I should add, it's not something that we've been able to look at during this project, but it's something quite attractive to look at longer term if we continue working in this area. Right, some sort of quick generic comments, nothing that you don't really know in terms of scaling from cell up to stack. You really establish as much as you can information at lab scale. I think you want to agree a fairly clear specification for what the stack's going to achieve and where you want to sort of the point around which you want to try and optimize the performance of the system. You do some outline stack design, looking at size, orientations, manufacturing methods, and then particularly around sealing and assembly. Those are some very, very key aspects of it. And you prove that work by experimental work at single cell and short stack level. You'll ensure, parallel with that, you're going to ensure that you can that the properties you're expecting from lab scale actually scale up to stack level in terms of variation in felt properties and all the contact pressures and things that you require to get a good low stack resistance there. You want to be looking more in detail at the internal flow system. So in our case, that's been looked at by University of West Virginia and PinFlow, where you're looking at the fluid, the fluid design and the leakage currents, and you'll then incorporate that into the more detailed stack design and manufacture that at sort of proper stack scale, and with and then do a number of revisions around that, because it's unlikely it's going to be perfect first time. So that's my sort of general higher level comments there. In terms of HIGREW, our sort of ambition at the start was fairly high, and we were looking, to try and do a stack design to minimise internal resistances and shunt currents and give you a design that's inherently low sort of cost. We're trying to keep the electrical specific resistances down to very low levels, low pressure drop, low shunt currents, and ideally come up with a stack design and manufacturing route where we've got the potential at megawatt scale to give you a low power per kilowatts cost, and also to try and demonstrate this at 5 kilowatt within the project timescales. Our initial approach around to try and do all this sort of challenging objectives was to use a sort of a design for manufacturing approach, particularly using the skills of a particular partner in the project at the time, a company called Heights, who had a lot of experience in injection molding, automated assembly, and with doing some work on vanadium redox flow battery systems. So they were really quite key to this, and the lower corrosivity of electrolytes gave us a lot of confidence in using things like thermoplastic elastomers in the injection molded stack, which we thought would give us some of this simplification involving sealing and assembly. And I can't really show you a lot of detail around that, because a lot of that work is perhaps connected with Heights, and I'll say something more about that in a minute. So, but because of the molding involved, you've got fairly fixed timescales to do with injection mold tooling, requiring you to commit to this at certain points and having done the design at certain points. So you need a sort of a freezing of the electrolyte and cell component properties to allow you to sort of fix on these things. And this was always going to be quite challenging as a way to sort of produce a stack at sort of month 24. This fairly tight time scale had a fairly significant hit from COVID-19 and the different complexities you've heard about with the electrolyte development, which make it quite difficult to freeze that specification. Also, there's a fairly significant impact on Heights. Unfortunately, we had to drop out of the project, which meant a loss of their fairly key skills, of which none of the rest of us could replace. So those two factors contributed to sort of changing really the approach with stack engineering project. So in terms of the HIGREW specific chemistry, the approach we've operated around there was to try and do more flexible stack development to accommodate the changes in the chemistry. And we decided to move, and it was agreed that we'd move to a more machine stack design. This allowed sort of more of a delay and further development of the electrolyte materials that went in. It allowed us more time for stack optimization within the development process itself, in terms of mixture of experimental trials and computational models. And it gives us a lot more time to actually learn about the operation of the stack and to demonstrate the actual HIGREW chemistry, rather than rushing forward to try and get a machine to get an injection molded stack, where we're trying to make decisions far too early, and we're probably end up with something that's very expensive but will work. And it also gives us the opportunity to try out some ideas we've sort of collectively got around sealing and assembly to try and cut the cost down in these stacks. Though the work we've just aligned, the flexible sort of work and development it's not really going to deliver a 5 kilowatt stack to Gamesa to operate in a demonstrator. So as you'll hear in the next talk, that's going to be achieved with a sort of commercial stack, accepting a commercial vanadium stack, accepting the limitations imposed by that around what it's actually designed for. But to make up for that, there'll be an extended period of characterization of the HIGREEW stacks by both ourselves and PinFlow.
John, you have the last half a minute, please. Can you go to conclusions?
That is my conclusion. I'm just concluding as to what I think we're going to be doing in going forward. So I'll stop now.
So thank you for the presentation and for really sharing at least some of the knowledge on how the stacks have to be designed. Maybe I will pose one quick question. Can you please comment on, let's say, the stack cost? You indicated that you'd like to get, let's say, below 500 euro or 600 euro per kilowatt of stack. Which component is the one which is most expensive in the stack construction? That means what are the key components in terms of the price of the stack?
I think with where we are, I think, well, I'll make the assumption that we'd have an injection molded design for the purposes of that. And I think for that, I think it's probably the bipolar plates. The bipolar plates, and yeah, I think it'd probably be the bipolar plates in this particular system, unless we can go to a cheaper non-carbon system.
Okay, so the bipolar plates are probably going to contribute mostly. And what about membranes? Are they also expensive, or what would be the share of the membrane to the stack cost?
I've assumed the use of the membranes that have been used within HIGREEW's development so far, and I think the cost of those was significantly less than using Graphite equivalents.
Mm-hmm. Okay. So thank you once more for the sharing of all the knowledge and once more for the presentation, and thank you for connecting. There were some technical difficulties, but we got in principle all the main messages from your talk. So once more, thank you. And let me now invite the next speaker, who is Michael Schäfer from Fraunhofer Institute, and he will talk about building of a new battery system like a jigsaw. So we are quite curious about your presentation. Please, you can, with the help of technical assistance, start your presentation. And then once everything is started, then the floor will be yours.
Yeah, hello, my name is Michael Schäfer. I'm a researcher at Fraunhofer Institute, and our work within the HIGREEW project is to basically assemble all the pieces that you already heard about and to compile it into a working system. And so the title of the talk is Building a New Battery System Like a Jigsaw. Credit actually goes to Uni Research for the title. But I liked it because this is often how it feels like when you. Yeah. This is often how it feels like when you put together a flow battery system, actually. So first, a couple of introductory slides about upscaling of flow batteries. Usually, what you start with is this kind of cell, laboratory cell scale. It has a very low threshold. Everyone can do it at a university with a relatively low budget. You can buy the electrolytes, even the cells you can buy at companies today. You can get quick results with a relatively low effort. But if you want to get to a real working system, you have to actually take those cells, make them larger, and stack them on top of each other to get a stack. And then you have something in a kilowatt range, so you can already power your homes, for example. John just talked about this in greater detail. But if you want to think about large-scale energy storage, and you have to take it one step further, take a lot of stacks, and then connect them to large-scale megawatt system, for example, as in this case. Of course, there are different approaches. Yesterday, we heard from companies who built smaller modules with integrated pumps and tanks, and then they just scale it up by basically repeating those modules. So it's more of a numbering of process. Actually, in this case, in our institute, we built a large-scale system where we put together a couple of stack arrays, as you can see in the picture on the right, and they are all supplied via one large supply line and one pump. I like this this quote by NASA, who concluded in their final report on their redox storage project that designing a flow battery to maximize system energy efficiency is a somewhat complex process. And I tend to agree, actually, even though most of the components are readily available, but fitting everything together can sometimes be quite a challenge. And so, for example, in this graph on the right, you see, if you remember the stack shelves on the right, you can actually see here the resistivity inside the individual stacks. If you follow the blue arrows, this is where how the electrolyte flows and how it's being distributed in the stacks. And you can see that if you don't supply enough electrolyte, then you will actually starve the stacks in the top rows, and you will have higher resistivity and lower efficiency. But of course, it's also about choosing the right materials. You have to take care of not only choosing materials that are stable when they come in contact with the electrolyte, but also materials that don't degrade the electrolyte itself. So, for example, in vanadium, you have to take care to not use any metals, because then you can destroy your negative electrolyte. And then one more point that is often neglected, actually, is finding suitable power electronics. I think my colleagues from Gamesa, they're experiencing this right now. Usually in flow batteries, you have relatively low voltage. You don't want to put together too many stacks in series to prevent shunt currents, but you still have high current and high power. So you have to find good solutions that are still efficient also. And there's at the moment not too much on the market. Okay, so what are the specifications of our prototype? We have quite an ambitious goal. We want to create a prototype with a power of 5 kilowatts and 20 kilowatt hours, so that's 4 hours of energy with a high efficiency of 80%. And we decided to put it inside a 10-foot shipping container. You can see on the picture on the right a test site in La Plana, where it's going to be located, probably next to those other containers just under the wind turbine, but you will hear about that later. So I can't really talk about current results, or at least not in the same scale that my colleagues presented, because actually we don't have any hands-on results to present yet. But what I can present is our planning so far. So we decided on the stack configuration. We fixed the piping design. Also, we selected all the components. And so we put a design freeze on the prototype. We actually had the hazard study just 2 weeks ago. And the current step is prototype construction. Okay, so starting with puzzle pieces. Like I said, we want to put a prototype in a 10-foot shipping container. So approximately 2.5 meters in every dimension. It's it seems like a lot of space, but you have to remember that we built a prototype, not a real product. So it's actually quite challenging to fit everything into the small container so that it's still accessible for maintenance. We want some thermal insulation in the container to keep the battery warm in winter, but also relatively cool in summer. We need electrical installations and also some sensors for temperature and gas. So the two main components are, of course, electrolyte and stack. So for the energy part, which is the electrolyte, we chose to go with a rectangular container, rectangular tank. They can be made relatively cheap from polyethylene or polypropylene. They will have double walls to comply with the safety regulations, and they will need to have enough space for thermal management, which I go into a bit more detail later. And of course, we also need some sensors for filling level, temperature, leakage detection, which will be inside the double wall. Then for the two stacks, as John pointed out, we will go with commercial stacks. Of course, they will still contain the active materials as specified in the project. They will be located next to the tank in plastic basins to protect from spillage, but also have some sensors for leakage detection just in case. Now we have to bring the electrolyte to the stacks, so we have to think about the pumps. Just very quickly, the two basic mathematical relations that go into the pump design. You have the flow rate that's derived from Faraday's law, and you can then calculate the total pressure loss in the system. The main part of the pressure loss is here in the last summand. Basically, it's pipe friction, and in the pipe friction, and all the other friction in the system. And here, of course, the biggest part is the stacks, but the stack is, well, they are a given, so we still want to, but we still have control over the piping system, so we want to reduce pipes and bends and elbows, or reduction through sensors as a system integrator. And then if you plot the pressure over the flow rate or capacity, you get basically this red system curve. And now when you pick the operating point of your system, you basically just have to pick a pump with a pump curve that intersects the system curve above your operating point. So we chose to go with centrifugal pumps, probably vertical pumps. So it again, we can save some space in a small container. We put them on top of the tanks. Of course, some things that you have to consider for flow battery pumps. They have to have high efficiency, and of course, they have to be designed for continuous operation. As for the piping system, it's relatively trivial actually at this point. We use PVC. It's used in most flow battery systems, even vanadium. It's not very expensive. Actually, it's the cheapest one amongst the plastic pipes. It can be handled easily. And of course, we still want to do some compatibility testing. This is what's being done by CTEC right now. They are testing various sealing materials also. And of course, here are the most important sensors for pressure, flow rate, temperature, to control the flow rate of the electrolyte. Then we also need to remove some heat from the system. I realize this formula is not, okay. And we have very approximately, you can calculate the heat generated in the system by basically multiplying the current in the stack with over voltage. And then you know how much heat is being generated. Then you can basically divide it by 2, and you have your heat exchanger cooling power, if you assume that heat exchanged or is distributed equally between the two sides. And we will be going for submersible heat exchangers. As you can see, we might want to put them inside the tank, also again to save space, and also because it's actually quite a cheap solution. And then, of course, you need some kind of cooling device, which in our case will be a recirculating chiller, which will be located on top of the stacks. Then one of the more difficult parts actually is gas blanketing. So as you heard earlier this morning, also in the organic flow battery, we have a similar problem as we have in other flow batteries, that we don't want our electrolyte to get in contact with air. So we have to shield it somehow. There are different solutions, for example, with oil or with nitrogen or other inert gases. So we will be going with nitrogen, and we'll have some kind of water trap or oil trap to keep the as a overpressure valve basically, and to keep the air outside of the system. Then almost the last point is power electronics. As I said before, it's not so trivial to find good power electronics for flow battery systems. But of course, there are some solutions. The problem with flow batteries is usually that you have a relatively wide voltage range. So, most converters, they work most efficiently if they have a narrower range. But then, of course, we need some other electrical installations, like the power supply for all the electrical components, and the control system, the battery management system, and also the electrical appliances. Right, so this was the overview of our plan at the moment. Like I said, as you can see, it's mostly 3D drawings at the moment. We are still in the process of finalizing our plans. And so at the moment our work is actually not so very interesting, as we are looking for components. We are preparing all the procurement of all the components, like the container, the stacks, tanks and piping system, but also all the individual sensors, so that's a lot of orders. Then the next step, of course, will be the construction of the prototype, which will begin soon. And then finally the commissioning and testing of the system. So we will start with some early system tests without electrolyte, and of course then follows the performance testing and characterization. So hopefully in the next workshop we can present with some more interesting results. That was it. Thank you for your attention.
So, Michael, thank you for the really interesting presentation of the entire system. Maybe I will start with the first question. Typically, investors are interested not just in the cost of the system, but also in the maintenance. Mm-hmm. So how difficult is going to be the maintenance, and how frequent? For example, when you are driving a car, you have to check the pressure in your tires or replace tires every few years and so on. So what about in these redox flow batteries? How frequent the maintenance shall be, and what everything shall it include?
That's a good question, actually, and something we want to find out during the course of the project. As I try to point out, we are planning the container so that everything is accessible, so we can easily change. For example, if the pumps have a failure or some of the sensors, we can easily exchange them. There are some automatic maintenance procedures, I would say, like, for example, mixing of electrolyte. If we can do this automatically or at least remotely. Everything else, I think we have to see how it will work out in the end. I don't expect there to be too much maintenance in the beginning, but usually as those systems run for a longer time, problems start to pile up.
Michael, nice presentation. You talk a lot about sensors. I was wondering about the sensor for measuring state of charge. How is that going to work?
That's a very good question. Yeah, that was actually missing from the from the presentation. I realized only this morning. I wanted to point it out, but I forgot. Yes, of course, we need some kind of sensor for state of charge. So we will just go with a kind of reference cell. So an open circuit voltage cell, which will be connected to the pipes in parallel, basically fluidically to the stacks, but without power supply, so we can measure the open circuit voltage of the electrolytes.
So Michael, the next question is going to be from a chat.
Yeah, Adam had asked, how do you ensure good mixing in the tanks?
How we perform the mixing?
Yeah, mixing in the tanks, so about dead zones in the tanks, how do you ensure that you get a good mixing in the tanks?
How we can ensure? Okay, yeah, so there are actually no mixers in the tanks, yes. We basically rely on the fact that it's still not very large tanks. We hope that there's not a lot of layering happening inside the tanks, and we also have I would say relatively high turnover through the pumps. So also one thing we have to observe, of course, but at the moment we think that it should be enough.
So thank you once more for the presentation, for clear answers to our questions. And now let me invite the next speaker, who is going to be Ait Marka from Gamesa Electric Company. And it's going to be a talk about techno-economical analysis of redox flow batteries and these systems. So the technical assistants will help you to start your presentation.
Hi, good morning, everyone. First of all, I just want to thank Pilsen for this great opportunity of hosting this event after a long time of in-person workshops or events. So really big thank you. And I'll move to my talk, which is about techno-economic analysis. My name is Ait Marka, engineering consultant for energy storage solutions in Gamesa Electric. So my talk, compared to the previous ones from my colleagues, it's not that technical, but it's definitely a very important aspect of our HIGREEW project. So I'll start with an overview. So I'll talk a little bit about the highlights from the LCBAT 4 RFP from the European Commission, which is basically the call for the HIGREEW project alongside other projects for the development of the redox flow batteries. I'll go through the LCOS metric, also what type of data we require for the techno-economic analysis, and what's our approach in HIGREEW. And after that, I'll list potential risks to achieving our project targets, and I'll end this with a summary. So some highlights from the LCBAT for 2019 RFP. So yesterday, at least 3 speakers touched on the topic of cost, which is quite important alongside other aspects for developing flow batteries, like safety, having a high-performing product, and also sustainability. And here you can see basically a part of this call, saying that cost is the most important driver for grid-scale electricity storage. And they're mentioning also the levelized cost of energy, or energy or storage in our case, which is measured in euros per megawatt hours. And then also listing the expected impact that our project, alongside the other projects from the LCBAT 4, should be having. Basically putting the energy storage cost on the path to fall below 0.05 euros per kilowatt hours, or 50 euros per megawatt hours by the year 2030. So what we are trying to do in the HIGREEW project is defining an interim target by project end, in a way to try to achieve the objectives of the European Commission. So as a conclusion for this slide, so cost competitiveness goes hand in hand with having a high-performing, sustainable, and safe product. You have to have a competitive solution so that you can be able to introduce it in the market. All other parameters or aspects that I have said, they are important, but cost is what drives the product into the market. So How is this basically evaluated? It's the L-cost metric, or levelized cost of storage. So here's a simple definition here. It's defined as a cost of kilowatt hour or megawatt hour electricity discharged from a storage device when accounting for all costs incurred and energy produced throughout the lifetime of a device. So just for sake of simplicity, you try to calculate the total costs of your project during its entire lifetime and divide it by the total energy discharged from your energy storage device over that period of time. Of course, you need to take into account a discount factor for the project lifetime. And it's basically the metric that is used to evaluate or decide if one energy storage asset is more or less competitive than another one. So let's go to the important part. I mean, we need to have an L-cost model that needs to be fed by certain type of data. And although we, as Gamesa, are leading this task, it's a collective work, and we are working closely with all partners in this task to try to make sure that we get a competitive product or competitive prototype. And basically here I'm listing or I'm categorizing the type of data that we have in 3 categories. So number 1 is technical info, and then a cost-related info, for example, for in this case for the product, and also project-related info. So in those categories, you can have some aspects that could be applicable to the other categories, but it's something really normal because it's an interrelated. All parameters are interrelated. So let's start with the technical information. Energy density. So the energy density of the electrolyte in watt-hours per liter. So we are in contact with the party that is developing the electrolyte. We need to understand how much volume we are going to need so that we can get the energy that we want at the output of the battery. Second one is efficiency, and this includes efficiency of the stack, also of the converters that we have, but and not to forget also the auxiliary consumption of the pumps, the fans, and everything related to auxiliaries. And the next point is degradation. So are we going to have degradation of the electrolyte in its capacity or in the efficiency of the battery? This is an important aspect, and this is we need more time of cycling so that we can basically get this type of information. And then we have the residual value of the electrolyte. So for example, for vanadium batteries, we know that part of the electrolyte can be recycled, but is it the case for the organic electrolyte that we are developing? We need to find out actually, but we need to wait until the project end to see if there is any additional value of the electrolyte. Next, it's technical information, but it's also has consequences or influence on the cost, which is failure rate and potential replacement. So we need to know what's the expected lifetime of the components that we are selecting, and if there is going to be any potential replacement during product lifetime. This is to be taken into consideration, because at some points we need to evaluate between one option and another. For example, you can have a cheaper component that has a lower or a shorter lifetime versus another component which is more expensive but has a higher lifetime. And in this case, you have to use the L-cost metric to get to make a right decision. And then cost-related information for product, CapEx, or capital expenditure. So we have to include costs of raw materials, costs of the components that we are selecting, and then there's cost of upscaling. And we are working at lab scale right now. The objective of this battery is to get it from TRL 3 to TRL 5, but there are some complications and difficulties from going from 3 to 5 or even to higher TRLs. And then there are cost of modifications. I believe my colleagues have previously stated that sometimes we are picking off-the-shelf product, but we are introducing some modifications so that those components are compatible with our battery. And then there is also the operational expenditure. And in the third category, we have the project-related info, which are not directly related to the materials, but rather to the project where the battery will be deployed. So we have the product lifetime. We have the discharge duration. So we defined a 4-hour system for our HIGREEW battery, but we can also consider other scenarios for the battery through the analysis. And then number of cycles. So how many cycles is the battery expected to do during its lifetime? What's the availability? So we have to consider how many days per year needs to be taken out from the battery operation. And then we have logistics costs, which is a very important topic, especially nowadays, since we are having supply chain disruptions, but also which is leading to increase in logistics costs. Charging costs, it's a topic that was also touched on by some speakers yesterday. So you have to take into consideration the electricity cost that that is used to charge the battery. And last but not least, you have if you have any incentives or subsidy schemes, that has to be considered in the analysis. So what was our approach for HIGREEW? So we needed a starting point before we can define our CapEx and LCOS targets. So we used vanadium redox flow batteries as a benchmark for the targets that we have defined. Information came mainly from literature, but also from the wide experience of the consortium members who have already worked with redox flow batteries before. And then we are actually conducting 2 lines of analysis. The first one is for the prototype that we are developing, so 5 kilowatt, 20 kilowatt hours, kilowatt hour batteries. This is one stream, but also for an upscaled product, mainly focusing on a higher production volume. So, if you order more of a certain component, so if you have higher volumes when you're doing the procurement, it is expected that you can get to lower costs. And it is actually needed so that you can get to the targets defined by the European Commission. You cannot base your analysis on a very small prototype in this case. And then the final product optimization is really not part of this analysis, meaning that the final product that we are going to have for HIGREEW, we can introduce some optimizations or improvements to it, but it's not part of the, it basically needs another project to be able to find out. But of course we can do some recommendations based on the project findings in our case. And then the third point, it's really a continuous analysis. You don't do LCOS analysis or techno-economic analysis only once or twice in a project. So whenever you have an advancement, let's say in the technical or in the economic parameters, you have to consider it and really do the analysis one more time to see where are you at this time. And the last point here is the sensitivity analysis. So the LCOS metric, although it's one number, but you need to feed the model with multiple numbers, either for cost-related or for technical parameters. So they don't have the same sensitivity in the analysis. So you need to understand how sensitive each of those parameters is, and based on that you can make the right decisions. So what potential risks we have in achieving or not achieving our project targets? So we are dealing with a new electrolyte chemistry, so we are still facing, let's say, some challenges in order to achieve the objectives that we have defined in the beginning. So we are dealing with it like by every phase. I mean, once we have, let's say, new advancements in that field, we have to take it into consideration. Number two is high prices of components and raw materials. So this could actually affect the previous or the primary targets that we have defined for our project. We have tight project timelines. I believe all projects are dealing with this, and also there's limited project budget in a way to get to the target. And last but not least, you could have, or we could face also problems or risks in the product upscaling from going to lab scale, from lab scale to the prototype. So a summary to this talk: cost, and it really goes hand in hand with having a functional product, having it sustainable, and having it safe. And next, it's a way, techno-economic analysis, it's a way to keep track of the project targets. So we have to continue doing it from until project end. And I said this point already, but yes, we, as Gamesa, we are leading this analysis, but in the end, it's a collective work, and we need strong communication between the partners to keep the model updated every time. And the last but not least, so product modifications are evaluated on L-cost basis. So whenever we have to make a decision that is related to cost or to any technical parameters, we have to use our model. And that was it for my talk. Thank you very much.
So I thank you for the presentation, which was clear. Maybe I will start with the first question. So first, the redox-flow batteries are known that they have quite a high initial cost. You call it CapEx. What would you propose among the different, let's say, business strategies or business models, how to overcome the anxiety of potential customers from the initial CapEx? That means how it can be overcome.
Thank you. Actually, this is a very good question. We get it very often, actually, as responsible for the techno-economic analysis. So sometimes you cannot compete against other technologies in terms of CapEx, and that's why you have to use the L-cost metric to evaluate your selection of one technology or another. So sometimes, for example, the case of redox-flow batteries, you're having a high CapEx cost compared to other technologies, like lithium, as an example. But if you're doing more cycles, for example, with your battery, and you have lower degradation, this is a fact for redox-flow batteries compared to lithium, then you may be able to get or improve your L cost.
Yeah, maybe a small comment to the last part. In vanadium flow batteries, there is an idea to lease the electrolyte to lower the capex. So that's one, but maybe for organics that's maybe more difficult. I have another question about the techno-economics. The numbers that you get out is very much important about the starting assumption about the scale that you are going to apply. And you did not say about what scale are you aiming at for your techno-economics.
It's a good question, actually. It's we're aiming for tens of megawatts, but as I said, it's only reduction in cost in terms of volume, of higher volume production. So basically, when we are to ask for quotations from the suppliers, we are trying to get quotations first for our prototype, but then we are trying to get also forecasts for if we are gonna procure higher volumes of a certain component, how would this affect our cost?
Yeah, and maybe an additional question to it. As a benchmark, you use the vanadium flow battery, which of course makes sense. Mm-hmm. And yesterday we saw a lot of different projects with the LCBAT4 project, like which are all merged in the Flores project, and they all use the vanadium flow battery as a benchmark. So I now see actually that a lot of different partners in the different consortia are all doing the same thing about the vanadium flow, vanadium flow benchmark type of battery. Would that not be an idea in Flores to discuss about having a common view about the benchmark?
Yeah, I guess one of the reasons is because simply it's the most mature technology for redox flow, and we are trying to develop an electrolyte that can be competitive first with this technology, but then also with lithium ion. So this is the goal here.
So it may be one last question also for me. Typically, when you make this levelized cost analysis, there is a parameter which is typically called discount rate, which is of course connected to public policies and regulatory framework.
Yes.
Which policies do you believe could actually help the energy storage solutions, whether it's redox flow or other ones?
Well, there is a good question actually, and I said this in the beginning that you have to include it in your calculations, but it's not coming from I mean, there is a number that we usually use in our own analysis, and we are applying it also here to the HIGREEW project. But definitely, I mean, selecting one discount rate or another will affect your final value that you're getting from LCOS.
Mm-hmm. So thank you. Maybe we will discuss it in a coffee break in more detail.
Would be happy to do that.
So thank you once more for your presentation. Now let me invite the last speaker, who is Antonio Risco from the Siemens Gamesa Renewable Energy Company. And the last talk is going to be about La Plana hybrid facility plant and about all the facilities which are available at the site. So I will again ask technical assistants for help.
Okay, hello everybody. My name is Antonio Risco. I work in Siemens Gamesa, and I'm going to speak to you about the La Plana facility. La Plana facility is where we are going to do the final test of the HIGREEW battery. Okay, so I'm trying to explain you the main capabilities and characteristics, always focus on the HIGREEW project. Okay, La Plana was built in 2060. So we are working there for more than 6 years, and we have 3 main purposes. First one, as a test bench, we test different component assets and controllers, and very important thing is in a real environment. The second task is research and develop. We are very focusing in develop algorithms or energy hybridization and grid code protection and levelized cost of energy. And the last one is a commercial tool. We can show for whatever what can do in the company, not only in the control modes, but in manufacturing and commissioning procedure. So if you want to visit La Plana, please ask me. Okay. Okay. This is La Plana. Okay. The asset starting for the wind turbine. The wind turbine is a G52 and the nominal power is 850 kilowatts. But this turbine is used for a lot of departments in our company. And for example, have the latest fire security system or energy truss that increase the power up to 920 kilowatts. And next is the photovoltaic plant is 245 kilowatts. But is used for testing the degradation of the panel and test the impact of the clouds and the shadows of the blades. The gensets are for off-grid modes. There are 3 gensets for 222 kilowatts each one, and these are from MTU manufacturer. It's very important they have a very low minimum technical. It's very important for off-grid modes. Okay. Speaking about the loads, there are resistive banks and reactive system. The banks have a 1.1 megawatt, and you can use it in steps between 10 and 100 kilowatts. The resistive is a coil with a mobile ferromagnetic core. Okay. The most important topic, the batteries. We have both batteries, one of lithium, manufactured by Samsung. It has 143 kilowatts and 143 kilowatts per hour. And it's managed by a PCS, a Gamesa Electric PCS. It's an in-house hardware. Okay, and it can work in grid feeding, grid forming, and grid forming support. It means it can put energy into the grid, support a grid, or create his own grid. Okay. The other battery is a vanadium redox flow battery. It has 120 kilowatts, but 400 kilowatts hour. It's under test, but to be honest, not works very well. Finally, the switching center. This facility works at individual plants, and every plant, the voltage, the final voltage is 20 kilovolts. So in the switching center, you have a switchgear for every plant, and you can deactivate the plants where you are not going to use. Okay, this is our controller. Control all the assets and devices in the facility, and have 4 different modes. It depends on the quality of the grid. Off-grid mode, on-grid, and way grids, final virtual power plants. Off-grid is when you haven't any grid, so you need to create the grid with the genset or the batteries. In this case, the stability of the grid is the most important parameter. When you achieve the stability, you can control other parameters like levelized cost of energy or whatever. And this mode have special features like black start or zero diesel operation. Speaking about the on-grid is when you have a very strong grid. So your interest is produce a lot of energy or maybe help the stability of the grid. The modes, an operator have to choose this. It's in manual, but you have a lot of active power or reactive power control modes, like availability power, droops, or limits, whatever. Way grids is when you have a grid, but it's a way grid, so, and you need to cover a critical load. So the control can combine off-grid and on-grid modes in order to maintain always the load energized. And the virtual power plant is a control in a cloud that controls several power plants in different locations. Sorry. And the idea is maintain the stability of the grid, speaking about a whole country. When you are using a lot of renewable energy, is a very important topic. Okay. The network. Okay. I'm going to speak about cybersecurity. I have doubts about this slide, but I decided to speak about that because just these days we are seeing how damaging could be a cyber attack, okay? Because an important part of the war between Russia and Ukraine is fighting behind a laptop. So imagine if the civilian population have an horrible problems, and in addition, if you cut your energy, they can use the hospitals or the heaters or the cookers. So for us, for our company, cybersecurity nowadays is a very important issue. So I prefer to speak a bit about this. Models, okay. We have several models of La Plana in MATLAB, in this island, Homer, Transys, PVCs. All of them are have 2 proposals. Reduce the cost of the test, because test in a real environment is expensive, and the other, maintain the facility in a safe conditions. For example, testing in MATLAB, we found a critical failure in a battery, so we can fix it before go to La Plana. So, okay, capability test. If you remember, we have banks of resistor, reactors. We have a control independent for this, so you can program different scenarios for test whatever you want. And speaking about the data collection, yeah. two things, the measure system and the data storage. The measure system in this kind of facilities is very important, the accuracy and the speed of the measure. Okay, so we have 40 PM180 who can measure a part of the most typical, like voltage, so on, harmonics, the quality of the wave, and oscilloperturbographies. Okay, the data storage, all the data is stored in the measurement device and in a NAS. Okay, HIGREEW expected targets. Of course, our target is to test HIGREEW battery in a real environment. Okay, so we have three main tasks. Okay, measure the performance, charge and discharge, the speed of response in different conditions like summer, winter, bad quality of the grid, or pumps on, off, and so on. And finally, the state of health. Measure the degradation of the battery with a very long test. Okay, this slide is zero diesel operation is a special off-grid mode that trying to maintain the grid only with batteries. So it's one of the most demanding modes for the batteries. Okay, and we think flow batteries is a perfect technology to test with this mode because you can separate the energy and the power, so you can reduce the cost of the battery. And on the other side, you need to maintain the quality of the grid and the performance of the battery. So the control of the battery, the BMS of the battery for this mode is highly demanding. Okay, current results. You have to take into account in our task in this project are mainly in the last steps. So we are almost waiting for tasks, but we have some tasks already done. For example, the place definition, taking account the power connections, the communications, the network connection, the wind direction, and so on. And speaking about the material, we ordered the materials of the electrical cabinet. We did a preliminary design and a bit of materials, anticipating our tasks, trying to compensate the delays caused of the coronavirus. It's an important delay today. Okay, as I spoke before, the networks, the security are very important, so our network is already configured for granted the access for all the members of the HIGREEW project. You connect through a VPN, but only in a DMZ. We allow the data from this zone, but the rest of the network is completely isolated. And next step, the first one is the battery integration. The battery needs to work with the rest of the asset of La Plana, so it's important to work in the same conditions. So when we start to collect data, we parameter the inverter, the transformer, and so on. And we start work with the CIC in the control of the battery. Okay, the battery will be integrated in the TST and in the SCADA. And we have to define the control algorithms that will be developed in StateFlow and in MATLAB. And finally, when the algorithms are more or less developed, I start to program in the PLC. The PLC is in charge of the communication between the algorithms and the rest of the plant, like SCADA, sensors, actuators, and so on. So this is all for my side. I hope it's not very boring for you, and taking account the time it is, thank you very much for your attention.
So thank you, Antonio. It was definitely not boring, because it's always interesting to see the real demonstration plants and what is going on. So perhaps we will start with a question from Peter.
Hello. I've got a question for your black start capabilities. So do you have a kind of load management? Of course you have, but the question is then, how do you build up the grid again? So do you have priorities in which power source you will connect, or can you disclose it? I don't know.
Okay. If I understand well, your question is how we decide what assets start, right? Okay. The easy response is the price. For a very easy example, photovoltaic is cheaper than wind turbines. Don't need maintenance and so on. Then you have other possibilities like risk, or risk for your own device. For example, over temperature in the solar inverter. Okay, stop the solar, change the mode to the price to the security. And the third one is if an external operator, in Spain, Iberdrola, maybe you know it, asks you for change your mode because they need, I don't know, compensate the reactive power, for example. So you need to change the mode. And change for inverters, for example, the battery inverters can compensate more reactive than the solar ones. I don't know if it's clear.
Yes, it was quite clear. Maybe I will continue with questions also for myself. I already asked today one question about the maintenance. And since you have the vanadium redox-flow battery lithium-ion, do you keep some record of the maintenance and how really frequent it should be? And from time to time, anything can in principle broke or needs some service. Can you comment on it?
Yes, sure. Lithium battery don't have more maintenance in itself, but the chillers and all the devices around the battery, yes, need periodically maintenance. And speaking about the vanadium, it have a huge maintenance. Pump, pipes, mix before, because if the battery stay in a stop for a long time, you need to remix the electrolyte. Maybe you need to charge again or activate again. Yeah, the redox flow battery needs more maintenance than the lithium. Yeah.
Mm-hmm. Yes, and my understanding is that your site is something like a testing, because in the future it's very frequently described that the grid operator will have something like a virtual power plant, for example, that can include batteries of different types, maybe some sources, photovoltaics and so on, and there probably will be some quite a simple interface for a grid operator, yeah, and how to switch the required capacity or how to control the quality of the electricity in the grid and so on. So yeah, it's I know that you are research and development facility, and typically it's you go quite deeply into really quite a lot of complicated details. But is there already some simple interface available for grid operators?
Yeah, of course the size of La Plana we can't move the grid of the country, but yeah, we have the possibility to simulate changing the frequency or the voltage and try to return to the nominal value. Yeah. And it is possible. And of course, we use the battery, mainly the lithium battery, and into mainly use is like energy arbitrage, charge and discharge, or control of the frequency, help to the system to maintain the frequency.
Mm-hmm. Oh, thank you. So if there are no more questions, then thank you once more, Antonio, for a really clear and nice presentation. And now let me take the floor, because I will have some closing remarks and recapitulation of this workshop, or of the part of the workshop. So I have a few points. First of all, I shall not forget the acknowledgement to the European Union for financing the HIGREEW project. Without this support, this project wouldn't be possible. That means that it's really helping connect the academic partners, the small, medium enterprises, all the way up to the larger companies. So that's first message. The second message is why was this workshop held? Of course, it was concentrated on the energy storage and particularly on the solution of energy storage in redox flow batteries. Why are we doing it, this energy storage? There are in principle 3 reasons from my point of view. First is to improve utilization of renewables, that means photovoltaics, wind. Second is to make the power, the electricity, more stable and more secure. And the third is, if possible, to make also electricity cheaper. Then let's say the current price of natural gas is really prohibitive, and the batteries are already, let's say nowadays, only during these days, quite cheaper than natural gas. Maybe not in the long term, but at least in the peak times. So regarding technical solution, this project is about finding alternatives to vanadium redox flow batteries, which is a benchmark in redox flow batteries. And one of the alternatives are so-called organic redox flow batteries. Why are we pursuing some activities here? First of all, we believe that perhaps they can be cheaper. Second, we are not going to depend on some mineral sources like lithium or vanadium in organic redox flow batteries. This was just some intermediate presentation of the workshop of HIGREEW project. That means it's not the end of the HIGREEW project. We just demonstrated where we are as of now. That means until the end of the project, we still have quite a lot of time, and we can finish number of tasks and improve really number of the indicators that we presented today, and to really see whether the organic redox flow batteries can be the alternative to redox flow batteries, and when, whether in 2-3 years or whether we will need some further development and to really refine development of some details and to provide more technical solutions to some parts. So we were concentrating mostly on, let's say, the assessment where we are in terms of the performance, in terms of the energy density. To the general public, I shall remind that in the redox flow batteries, the energy density is not such a critical parameter like in mobile application, where the energy density per kilogram of batteries in electric cars or in smartphones, it's of course essential. In stationary redox flow batteries, because of their intended use, this parameter is important but really not essential. And of course, we were discussing also the potential for upgrading. So this was a recapitulation of the workshop, and now some practical remarks. This ends like the public part of this workshop that was held yesterday and today. Now everybody is of course invited for a lunch that will continue and for discussions in the lunch. After the lunch we are going to have a closed general assembly session of the HIGREEW project where all the members of the consortium plus advisory board will be present, and whoever is interested in visiting PinFlow startup company, then there will be excursion at 4 p.m. It will depart by buses from this place. So even if you are not a member of HIGREEW and would like to really see the facilities where the laboratory and some larger really commercial stacks are manufactured and assembled, then we will start at 4 p.m. from this place. In the evening, there is going to be another dinner. A preliminary meeting time, it's at 7 p.m. in front of the St. Bartholomew Cathedral. That means the same place as yesterday. And from this place, we will go to the restaurant. But the time of 7 p.m. in the meeting can a little bit change depending on how long the afternoon program and the excursion will take. But preliminary, it's 7 p.m. at the same place. So let me also thank all the online participants that were watching us. There were really frequently more than 100 viewers, online viewers that were really following us, and they were also actively asking questions. We were just able to ask during the discussions just a few of the questions from the online audience. So also thank you everybody following us. And I believe that purpose of this workshop was met. It means introduce the advantages and current pitfalls of redox-flow batteries where we are, and also identify where we still have some potential for improvement and for a wider adoption of this technology, which is really a serious contender in energy storage systems of the future. So thank you for everybody, and enjoy your lunch.